Hi, Algebra 2 students. This is the video of the first half of the practice test for Friday, December 4th. And it's our test of sections 4.1, 4.2, 4.4, and 4.5. It was before Thanksgiving, but remember we skipped 4.3. So this one says exactly what I had in class that we talked about earlier this week. Graph each quadratic function, name the vertex, axis of symmetry, the maximum or minimum value, and the domain and range of each function. And so what you want to do with the practice test is try and do these problems on your own first. So hit pause, try it on your own, and then start the video back up if you get stuck or if you need to check your answer. First thing is, this is in vertex form. Y equals A times the quantity x minus h squared plus k. So we probably want to start by saying what the vertex is. And we remember that whatever we see in the parentheses with x is always the opposite of what it appears to be. So it says x minus 2, that means positive 2 is where that x value is for our vertex. And then the 3 in the back is normal. K, HK, that's always our vertex. Now my axis of symmetry is a vertical line that always goes through the vertex. So when it says x equals, you just want to look at your vertex and you want to say, hey, that's what it is. It's 2 because the 2 is in the x position for the vertex. When we're graphing it, what we want to do is use y equals ax squared as our parent function. And in this one, since there's no a there, it's a 1. So what we want to do is graph y equals 1x squared. And we only have to do a few numbers because we know that this has symmetry. So I'll try 0, 1, 2, 3 just for fun. So 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. We get a look at our perfect squares that we've been talking about as we've been factoring. So we have a graph of 0, 0, 1, 1, 2, 4, and 3, 9. And then we remember that the parent is always going to be symmetric to the y-axis. So we can go equal but opposite on the other side of the y-axis. So that's just a matter of counting. Now that's my parent function. So that one is dashed or dotted, does not get the solid line because I'm not done yet. Why I'm not done? Because my vertex moved. This was vertex form, and my vertex moved to 2, 3. So when I think about the transformations, I realize, well, it went 2 to the right and 3 up. So I take those really nice points that I had, 0, 0, 1, 1, 2, 4, 3, 9, and I just count and move those 2 to the right and 3 up. And then I'm going to put in my new axis of symmetry at x equals 2 and use symmetry to go equal but opposite on the other side. And now I can draw in my solid parabola, which has been moved 2 units to the right and 3 up. Now the second set of questions that they have here about max, min, domain, and range, usually those are easier if we have at least a visual of the graph to look at. So we'll usually wait for those. This shows us this has a minimum. It has a lowest point. And the question is, where is that lowest point? And that lowest point is at 3. Because again, highest and lowest points are about the y value. So the lowest point there would be a 3. Our domain, all of our quadratics go to the right and left forever. They may not go super fast, but they go right and left forever. And our range, we see that our bottom y value here, our minimum, was 3. So that means we have 3 and everything above it. Y is greater than or equal to 3. And we've done everything they wanted. We graphed it, we named the vertex, the axis of symmetry, the maximum or minimum value, and the domain and range of each function. So again, when you're graphing in vertex form, get the shape from y equals ax squared. Just make a little table using numbers like 0, 1, 2, and 3. Then use symmetry to get the other side and move it according to the transformations for right and left and up and down. Here's another one. Graph each quadratic function. Name the vertex, axis of symmetry, maximum or minimum value in the domain, and the range of each function. But this one's not vertex form. There's no parentheses. This one's in standard form. So again, pause, try to do this one on your own, and then come back and start it up again so you can see what you should have had. All right, so with this one, A is -2, B is -12, and C is 11. And we have to remember the little formula x equals -b over 2a to get the x coordinate of the vertex. So the negative of -12 over 2 times -2 would give us 12 divided by -4, which is -3. So the x coordinate of our vertex is -3, and we might as well put that down right now for the axis of symmetry, because the axis of symmetry is what this formula is really for. But it always goes through the x-coordinate of the vertex, so you could use that thinking as well. So my vertex so far is -3, but I need to know -3 what? And to figure that out, I need to know the y value. And that's what that formula is for. That's for finding y's. So y will equal -2 times -3 squared minus 12 times -3 plus 11. Follow the order of operations. You need to do exponents first. -3 squared is 9, so -2 times 9. And then we can do the multiplication, but let's wait a second for that to make sure that everybody sees that you do exponents first. And then we'd multiply left to right. -18 plus 36 plus 11. -18 plus 36 is 18 plus 11, and y equals 29. So I've got a very large y value here. Now this is a test, and that means I can't just guess where -3, 29 is. On a test, sometimes you have to change the intervals. So right now, I can see everything looks like it's going by ones. But if I'm going to graph this, and I have 10 by 10, I'm going to need to go at least by threes on each one of these. So 3, 6, 9, 12, 15, 18, and you can just put a couple of markings on there to show that you understand that it's 3, 6, 9, 12, 15, 18, 21, 24, all the way up here to 30. The x's can stay exactly like they are, but the y's, we have to go by threes. And you might want to come down here and put a few negatives on there. To show that you're going by threes in the negative direction. So let's see, we've got a vertex at -3 and 29. So -3 and 29, right up there, almost at 30. And we have to figure out more stuff. I mean, that's only 1 point. That's not enough. Well, that's where our axis of symmetry is located, is at x equals -3. But we're going to need to make a little table. And it's always nice to put a 0 in there because you're going to get 0c, because this will be 0 minus 0 plus 11. So it's going to be 11. And that means I've got some more points that I could put on here. 0, 11 would be 3, 6, 9, and a little more about right there. And then I can use symmetry to go equal but opposite on the other side. So 3 units away from my axis of symmetry. Now, this is a test. So I don't know. I wouldn't feel good about just putting that on there. I don't know how wide my parabola is. So I take a look at this and I realize, well, I already know what 0 is. 0 was 11. Maybe I better try putting a number like 2 or 3 in here to see what I get. Let me try 2 since that's smaller. So that would give me -2 times 2 squared minus 12 times 2 plus 11. And You could just put that in the calculator, parentheses and all, but I'm going to go ahead and use the order of operations for it. 2 squared is 4. So negative 2 times 4 minus 12 times 2 plus 11. And then we'd go ahead and multiply left to right. Negative 8 minus 24 plus 11. So now we have negative 8 minus 24, which will be a negative 32 plus 11. Kind of running out of space here. So that will give me a negative 21. So at 2, I'm down at negative 21. 3, 6, 9, 12, 15, 18. And I can use symmetry to go equal but opposite on the other side. So I've got 1, 2, 3, 4, 5 units away from the axis of symmetry. 1, 2, 3, 4, 5 on the other side. Much better. I feel really good about this parabola now that I put that third set of points on there. So 2, negative 21. All right, now, max or min? Well, this one has a highest point. It has a max. And that max is whatever the y value is at the tip top up there, and that was from the vertex. So that's 29. Our domain, again, all real numbers. It's going right and left forever. And then our range, well, for our range, we can see the highest y value that we had was right here at 29, and we're below that. So y is less than or equal to 29. That was our cutoff. So that is a standard form quadratic being graphed. Like I said, this is very, very similar to what we did in class earlier this week. Now, the third one here is talking about without graphing. Now, that doesn't mean you can't make a sketch. It just means don't go through and, use one of the negative 10 to 10 drawings that we had on 1 and 2 and find this. Without graphing, name the vertex, axis of symmetry, the maximum or minimum value in the domain and range, and describe the transformations of the function when compared to the parent function, f of x equals x squared. First things first, I have to look at it and notice it's in vertex form. And I want to think about what that means. So, my vertex is going to be at 3, 2, because again, whatever's in the parentheses with the x is always the opposite of what we think it should be. And that gives me my axis of symmetry at x equals 3, because the x coordinate of the vertex is 3. Now, to answer these other questions, I have to know whether or not this is going to open up or it's going to open down. And to know that, all I have to do is look for that a value. If it's positive, it opens up. If it's negative, it opens down. So this is where I said you might just want to make a little sketch. You don't have to graph it totally to know what's going on. So we know it opens down. That means it has a highest point, which is a max. And that highest point is the vertex. So the y value to explain highest or lowest is going to be our maximum value. Now the domain, we already know that our parabolas are all real numbers. They're going right and left forever. And for the range, you might want to just do this. Label that so you can think, okay, so 2 is the highest y and we're below that. So y is less than or equal to 2. And you do all that without having to graph it. You just have this little sketch, whether or not the sketch is in your head or it's on the paper. Now transformations, that's where we have to describe all of the numbers that show up in this formula from left to right. So the first thing we encounter is a negative, and that means we will reflect over the x-axis. And then we see a 4, and we know that if a is greater than 1, that's going to be a vertical stretch. So vertical stretch, factor of 4. If it's a fraction between 0 and 1, then it's a vertical compression. And then we had our vertex, which normally for the parent function would be at 0, 0, but it was moved to 3, 2 because this x minus 3 means translate 3 units to the right and the plus 2 in the back, 2 units up. So again, be careful about what you see in the parentheses with the x. Make sure you explain that as an opposite as you go through there. And doesn't require having to have the graph. We can get a little picture in our head, a little sketch in our head, and we're good. All right, number 4. Now, this word problem, but I start to think, well, that's not a really big deal. I mean, if I look at this, I see they gave me the formula. The formula is what's important. The formula is for a parabola. So the students in Mr. Wilson's physics class are throwing golf balls. Okay. The flight of group A's ball is modeled by the equation y equals negative 0.14x squared plus 0.68x plus 6, where the height y in feet can be written as a function of x time in seconds. Okay. A says, when did the golf ball reach its maximum height? All right, so it was good that I thought about this as a parabola because it's got a negative in front of the x squared, which means it's going to go like this. So if I want the maximum, I need to figure out that spot right there. Oh, wait a second. That's the vertex. We know how to find that. This is in standard form. And you find the x-coordinate of the vertex by using negative b over 2a. So I'll have to do negative 0.68 divided by 2 times negative 0.14. So that's going to give me the x value that I have for my vertex, and that is 2.43 seconds. So that answers their question, because their question was, when did the golf ball reach its maximum height? And up there it said that x is time in seconds. All right, what is the maximum height? Oh, well, that's the y. We were talking about that when we went ahead and did the last 2 problems. So that means I have to take my little 2.43 seconds and put it back into the original equation. And I can just use a calculator to crank that out. So if you use the parentheses and put it in the calculator exactly like that, it comes out to 6.83 feet. So the vertex is where all this came from. My vertex is at 2.43 and 6.83. That answers questions A and B. Now C says, Bobby throws the golf ball to Connor, who makes a spectacular catch of the ball 6 feet above the ground. How long was the golf ball in the air? Oh, so I'm going to have to put the 6 somewhere in that equation and then figure out what the x-intercept is. All right, 6 feet above the ground. The height y is in feet. So I'm going to have to put that 6 over here for y and see what happens. Okay. Well, what they're really asking me to do here is figure out where this is hitting the x-axis, because that's the ground. And to do that, we just spent a couple of days finding the x-intercepts, which are the solutions. And solutions are zeros. Oh, I got to have a 0 on one side. I'm going to subtract 6 from both sides. Ew, it has decimals. It does, but we can still solve this by factoring. In fact, if you look at this for just a second, you're going to see, hey, there's an x in both of those. And really, to solve it, that's all you had to notice. So what you'll do is you'll take an x out, or in fact, let's take a negative x out in this one because we have the negative in front of our x squared term. So negative x, and this will leave us 0.14x minus 0.68. And now this one we know would be a 0, and that makes sense because before they've thrown the ball, they're at a height of 0. This one is the one that's going to give us a numerical answer, a number for our 0. So we would add 0.68 to both sides. And we would divide by 0.14. And we'd grab a calculator and get 4.86 seconds. So questions about the maximum or the minimum are always the vertex. But solutions, when they give you a number to put in, that has to do with figuring out where your x-intercepts are, which are your zeros. So easiest to just factor that and get your 4.86 seconds. Next problem says, to make an enclosure for chickens, yep, love chickens, a rectangular area will be fenced. Oh, we learned in geometry, draw pictures. A rectangular area will be fenced. There is 120 feet of fencing material. Oh, so all the way around, they have 120 feet. Okay. A says, what quadratic function represents the area of the rectangular enclosure? Oh, so now we've got to do some thinking. Let's see, because I can't just put x's and y's on here. I'll have two variables if I do that. Well, let me start here. And I realize that that 120 is made up by 2 times the width plus 2 times the length. So I'm going to let my width be x. And if I don't want two variables, I'm going to have to get this L all by itself so that I can write something down that has x's in it for the length. So I'd subtract 2x from both sides. Then I would divide everything by 2. So L, the length, is going to equal 60 minus x. Now I can put this back up here. And I don't have two variables. If you look at my picture, I have x's all over the place. So when they ask what quadratic function represents the area of the rectangular enclosure, rectangles are length times width. So area equals x times 60 minus x. Now, I don't know what the area is yet. All I know is that that's what would do it. And I could certainly distribute this and turn it around so it's in standard form. Now, B says, what dimensions will maximize the area of the enclosure? Maximize, huh? Well, this is a negative x squared. Oh, if I just find the vertex, I will have the answer. And it's in standard form. So x equals negative b over 2a. A is negative 1 and b is 60. So this will be negative 60 over 2 times negative 1. And that will be negative 60 divided by negative 2, which is 30. So the width will need to be 30, and this was in feet. Now, it said what dimensions, so I need the other one. And all I have to do is take my 30 and put it in for x. So 60 minus 30, well, that's 30. So the length and the width would be 30 feet. So the dimensions, 30 feet by 30 feet. And that's a question that appears a lot on ACT tests, where they say, what would the maximum area of this rectangle be? And you need to know, it's always a square. It always is. So 30 by 30 gives us our little square there. Next page, we start with factor completely. So number 6, x squared plus 4x minus 12. You go through that mental list of, is there a greatest common monomial factor? Nah, nothing I can pull out of all of those. Is it a perfect square trinomial? No, negative 12 is not a perfect square. So it must be good old-fashioned factoring. So I'm looking for two numbers that multiply to negative 12 and add to 4. X plus 6 and x minus 2. Going to 7. Greatest common monomial factor? Well, let's see. For 9, it could be 1, it could be 9, it could be 3. Nope, that's not going to divide into that little 4 in the back. But wait a second. 9x squared is a perfect square, and 4 is a perfect square. Maybe this is a perfect square trinomial. Let's check it out. 3x times 2 is 6x, and when you double it, you get 12. So that means we can write it as a binomial squared, and we just said what has to go in here, a 3x and a 2. And then we look at the middle term, and we realize, oh, going to have to be a subtraction symbol in there, because it has to come out to be negative for the middle term. Number 8. Ooh. Negative x squared plus 17x minus 72. Well, first things first, that negative can't be there. So even if we can't pull out anything else, we have to pull that negative out and factor it in front. And we can't pull out anything else, so pull that out and change all the signs, because when you pull a negative out, you're really finding the opposite of everything that you had to begin with. Now, perfect square of x squared. 72 is not a perfect square. So we'll go to good old-fashioned factoring. X times x obviously will give me x squared. But I need two numbers that multiply to positive 72 and somehow add to negative 17. Hopefully, negative 9 and negative 8 jumped out at you. And it doesn't matter if you put negative parentheses x minus 8 parentheses x minus 9, because multiplication is commutative. Going to number 9, I notice the same thing. We've got a negative, so I can take at least a negative out of this. But let's see. 5, 30, and 25. Hey, 5 will go into all of those. And, oh, they all have an x. We can take an x out as well. So now I would need the y squared, so that negative 5x times y squared will give me negative 5xy squared. And I will need a plus 6 and a y, so that negative 5x times 6y is negative 30xy. And then I will need plus 5, because negative 5x times 5 will give me minus 25x. So far, so good. And make sure you use y's with this one. We've got x's and y's, so you have to stick with the correct variables. Now, I might not be done. Not a perfect square trinomial. I know that because 5 is not a perfect square. So what I have to do is try to find two numbers that multiply to 5 and add to 6. Oh, that's 5 and 1. Factored completely. We have no more squareds anywhere in any of these for 6, 7, 8, and 9. And that would be a good place to stop on Friday, leaving us with 10 through 15 for Monday to work through. So watch this over and over again if you need to, but be prepared for questions very similar to these. This is the review assignment for the first day of review for the test of 4-1, 4-2, this is mislabeled up here, 4-4, and 4-5 day 1. So from pages 268 to 270, do 4 through 11 and 13 through 16. And this is also in Schoology and on campus if you lose track of these problems.